Okay, so I'm not presenting alone today, as I'm presenting with Salman, my colleague. So my name is Markus Bosch. I'm working at Infineon since 2008. Since 2014, I'm focusing on IP and block level verification using Specman and SystemVerilog.
Hi, I'm Salman Tanvir, and I work as a digital verification engineer at Infineon in Duisburg, Germany. And I'm involved in IP and SOC verification using both simulation and formal methods.
So we agreed that we would like to use our recording for the session. I don't know if this information was passed to you.
Yeah, that's fine. I will share it.
Okay, thanks.
Just make sure that you see my screen and the voice is clear for you.
The topic that we would like to present today is make your test benches run like clockwork.
Our agenda contains the following points. Initially, we want to explain why we think a clocks UVC is an essential component in any verification environment. We will state our motivation and present the advantages of using a generic clocks UVC. Afterwards, the architectural aspects of the developed UVC are explained. Finally, we will summarize our results in a conclusion, present some recommendations, and give you the chance to ask questions in the Q&A.
So why do we need a clocks UVC? Handling of clocks is an integral part of verifying any synchronous IP. Frequently, test benches manage clocks in an ad hoc fashion. A more efficient way would be to develop a generic dedicated clocks UVC that can be reused in every project. This is especially helpful when working with complex IPs with numerous clocks that are related to each other. We consider the clocks UVC as an essential component of any test bench on par with interface and sideband UVCs.
Our motivation is to outline a UVM clocks UVC architecture that fulfills the following requirements. The UVC must be generic enough to be capable of handling any number of clocks. The UVC should be reusable across multiple projects. It should be able to generate a reference clock with configurable timing characteristics and any number of derived clocks. Integer and fractional division should be possible. Dynamic clock reconfiguration should be possible without introducing any artifacts. Monitoring functionality should be provided for each individual clock. The BFMs should be reusable in both SystemVerilog and Specman class-based environments.
Where do we see the advantages of using a generic clocks UVC? One major point is that clocks can be handled in a common and unified way. It gives a consistent look and feel for all projects. This fosters reusability and portability. It also saves time. No painful reinventing of the same thing in multiple projects is required. By sharing a single UVC with a wide user base, we also think that a high code quality can be achieved.
This section describes the architectural aspects of our proposal. We will first explain how the transactional and signal level parts of the UVC are partitioned. This is followed by an explanation of how the transactional part of the UVC connects to the design under verification. We then show how the transaction item as well as the configuration objects for the UVC are modeled. This section ends with an explanation of the driving, monitoring, and checks infrastructure.
As you can see, we have structured the UVC into two parts, a transactional class-based part and an interface-based BFM part. The class-based part is henceforth referenced with the abbreviations HVL for Hardware Verification Language and the BFM part with HDL for Hardware Description Language. The motivation behind the split is to be able to reuse common code in both SystemVerilog and Specman environments. The HDL part, which contains the core of the UVC, for example, driving, monitoring, and checking, is implemented in SystemVerilog and can be integrated with different configuring HVL layers, for example, SystemVerilog or Specman. The HVL to BFM connection is explained on the next slide.
Typically, virtual interfaces are used in SystemVerilog for HVL to HDL connections. However, as virtual interfaces are type-specific, parameterized clock interfaces cannot be referenced using a common virtual interface. We opted to use the already known polymorphic interface mechanism, which allows the referencing of multiple interfaces via a single abstract class handle. In this approach, an abstract class is used to define an API that allows access to the interface signals via accessor methods. This API is implemented in a concrete class, which extends from the abstract class and is part of the BFM. This way, we can access any specialization of the parameterized interface with a single abstract class handle.
Here is an overview of the architecture showing both the split transactors and the polymorphic interface together for SystemVerilog. The HVL side holds an abstract class handle which is referencing a concrete implementation in the HDL BFM.
For Specman, the BFMs are the same as in SystemVerilog, with the exception of the API. Here, the abstract class approach is replaced by the Specman DPIC mechanism. The API methods in both the HVL and HDL parts are qualified by the import or export directive, depending on the direction of communication. Data is passed between the two parts using a packed struct.
In order to configure the BFM agents, from the HVL part, multiple class-based configuration objects are used. These objects are passed to the BFMs via the testbench to DOV connection mechanism, as explained earlier. They are translated into packed structs before passing to the BFMs, which is required for the Specman DPIC mechanism, but would also enable emulation if required. The driver contains one configuration for the reference clock and one for each derived clock. The monitor uses a separate configuration object for each monitored clock.
Here is an overview of the different configurations and the provided control knobs. The reference clock low and high time are individually configurable via the phase width knobs. Additional control to gate the clock and to introduce jitter is provided. For each derived clock, the starting polarity and phase shift with respect to the reference clock can be configured. If disabled, the clocks can optionally be driven to high impedance. The dividing ratio and resulting duty cycle and period can be configured using 3 modes. These will be explained in the next section. Each clock can be labeled with a string identifier for ease of debug.
The complete driving functionality is encapsulated in a driver BFM that generates a reference clock and a parameterized number of derived clocks within dedicated processes. The BFM is initialized using the HVL configuration objects before the run phase. Any further updates are done using the standard way using sequences. The sequence item encapsulates fields to select which clocks to update, the desired timing characteristics, and additional sequencing knobs. The sequence first updates the agent configuration and then pushes it down to the BFM.
The reference clock process uses the timing characteristics set by the configuration for generation. It can be gated, which is activated in the low phase of the clock. As a consequence, all derived clocks are stopped. To ensure that the derived clocks are starting with a defined state, they are initialized at the beginning of the reference clock process.
The reference clock process also provides the possibility to introduce jitter. We use a simple jitter model which only varies the high clock phase. The jitter is applied as a percentage of variation that is randomly added or subtracted from the ideal high time. The figure illustrates a variation of 5% being applied on the clock period, which would result in a maximum cycle-to-cycle jitter of 10%. In case the jitter is enabled, it also propagates to all derived clocks.
All derived clocks are generated in a dedicated process which is sensitive to the reference clock. As described earlier, 3 different driving modes are supported: sequence patterns with configurable high time, and edge counter. These modes will be explained in detail now.
In the sequence pattern mode, the derived clock is generated by iterating through a bit pattern of up to 128 bits on every reference clock rising edge. The pattern is decoded MSB first. If a 1 is detected in the pattern, the reference clock is propagated through, otherwise it remains low. This provides a flexible way of specifying the derived clock as an arbitrary pulse sequence, which also can be used for fractional division. As seen in the figure, the derived clock is following the specified 22-bit sequence pattern. This happens to result in an average dividing ratio of 3.14. The derived clock can also be phase shifted, which is supported in all modes.
The next supported mode is sequence patterns with configurable high time. It is similar to the previous mode with the exception that the high time is configurable. Here, in this example, the MSB of the pattern is 1, and as you can see, the derived clock goes high on the first cycle and stays at this level for the configured high phase duration. As the pattern is 3 bits, this sequence repeats after every 3 reference clock cycles. This mode can be used to freely adjust the duty cycle of the derived clock.
In the edge counter mode, the high and low times can be individually configured by providing a count for the number of reference clock edges for each phase. The count includes both positive and negative edges.
The clock's timing characteristics can be triggered to be updated at any times. The desired settings are first loaded into shadow registers, which are mirrored into the derived clock configuration registers at a synchronization point. This is done to avoid any intermediate artifacts on the clock. The synchronization point can either be a reference clock rising edge, or when all derived clock periods align. In the latter case, the new configuration is applied to all derived clocks at the same time. However, if the periods cannot align, this feature should not be used. The figure depicts the update being applied when all clock periods align.
The monitoring is implemented in a parameterized HDL-BFM, which consists of a dedicated thread for each clock. The time period and duty cycle is measured for each cycle, and a transaction is published whenever a change is detected. In cases where the clock characteristics will change frequently, for example, fractionally divided clocks, or when jitter is enabled, the publishing can be disabled. Alternatively, the BFM provides a monitoring task that can be called on demand. The measurement window can be configured, and the task returns the measured duty cycle and time period for each cycle of the window, as well as an average. An additional utility task is provided that enables the user to synchronize with an edge of any clock. The edge count and polarity is configurable.
The monitor BFM also provides two checking tasks. One can be used as a clock watchdog to ensure that a clock does not get stuck unexpectedly. Similarly, an inverse check is possible to detect when a gated clock has activity. As the monitor transaction encapsulates the timing characteristics of each monitored clock, any further checks can be implemented at a higher layer.
We have developed a fully functional clocks UVC with a diverse set of features. The SystemVerilog version is complete. For Specman, the concept for integration with the SystemVerilog BFM is proven. However, the full implementation is currently ongoing. The implementation is done in a generic way and can support any number of clocks. The code set is kept to a minimum by using a common HDL BFM base for both SystemVerilog and Specman. The different driving modes provide a very flexible way for generating derived clocks. This includes the generation of arbitrary pulse sequences and support for integer and fractional division. The UVC allows switching of timing characteristics without introducing any intermediate artifacts.
For monitoring, the user can optionally enable automatic monitor transaction publishing or pull measured values by calling a task. Checks are implemented to detect when a running clock gets stuck or when a gated clock toggles. We think that the implementation can be optimized with the following improvements. The simplistic jitter implementation could be enhanced. The automatic monitor publishing is currently sensitive to any change. This could be improved by adding a tolerance window that would allow automatic publishing for clocks with jitter. Currently, time period and duty cycle checks are left to be implemented on a higher layer using the monitor transactions. This could be built into the UVC. As the UVC can monitor any number of clocks, relationship checking between clocks could also be added.
We would like to thank you for your attention, and if there are any questions, we would be glad to answer them.
Okay, Marcus, thanks for your presentation. Do we have anybody any questions? So now we have 10 minutes for that. So please feel free to raise your questions.
Right, so I think we have one question. Marcus, do you want to take this? For how do you handle time, scale, and precision?
Oh, Salman, can you hear me?
Yes, I can.
Okay. So yeah, time scale is defined by the time unit, yeah, and time precision. So this is how we are doing this, yes?
So basically, all of the knobs were basically integral multiples, right? So you scaled the simulator time unit basically. So you could, I think by default it's 1 picosecond, but you could also scale that as required, right?
Exactly. Yeah. Yeah, as we mentioned earlier, so we also have labels on the clock signals for ease of debug, exactly as a string.
So
I think we are doing this. Maybe Salman, do you want
yeah.
to answer?
So that was also my feeling. So basically, we mentioned that the monitors are always running, but they only publish when a change in the measured value is detected, right? And this was probably one limitation, because if you have jitter, or if the period is changing because of fractional division or anything, then you will not, you will get basically heavy traffic, right? So we have a knob that basically can configure the monitoring. So in those circumstances, you can switch them off, and then alternatively have on-demand pulling. But it already considers that, yeah, the clocks are always monitored. Yeah. And that's one of our recommendations, that, okay, we need to probably improve this in terms, if we have then jitter clocks, or yeah, clocks with changing parameters, that, yeah, this can be compensated with a tolerance window, and then, yeah, it also could be improved, basically. Yeah.
Yeah, and if in case the clocks would stuck or toggle unexpectedly, there are also checks for this, yes. I think for the next question, this means your value definition on the upper layer sequence depends on the simulator timescale settings. This is currently the case. Yeah. Do you have a solution for generating a reset? So initially, this UVC had also a default reset, yes, but due to the fact that we are using a sideband UVC for reset generation, we have not mentioned this feature anymore. And it maybe would also make sense to have a dedicated reset UVC for IPs with complex reset scenarios where you have dependencies and loops.
So Marcus, correct me if so I think this is not open source, right? Because we
it's
use some, yep.
But I think with the information that we provided, it should be quite simple to implement this.
So we still have 5 more minutes to left. So again, a couple of new questions. Thanks for that.
So for the second question, the UVC is not yet power aware. So yeah, this could also be an update, right?
So I think we have not encountered any performance issue up to now, yes. So So for the UPF, I think it would also be easy to implement this because you only need the the state of the UPF state of your particular clock, and then you have to gate the checks with this. I think this would be easily possible. So somebody raised the question if we will be in the virtual world to discuss further. So I'm not able to attend. So if there are questions, please just write an email. So I will be happy to answer questions.
Okay, if there are no further questions, then let's end this part of the session. Thanks for your presentation.